Today we are going to do section 3.6 and section 3.7. The reason for that is because turn out section 3.6 is a very short review of the absolute value function, which we have already done, as I will demonstrate. So I'm just gonna assign you 2 examples. The whole section has only 3 examples, and we're going to skip the first one. So the example 2 just means that we're doing exactly what we did in the previous section, in the last section 3.5, where we do this type of thing. Okay, what do we do? Vertical stretching, right? Moving stuff up on the other side, and moving stuff to the right, that sort of stuff. And that's what we are going to be doing in example 2. So please do that example yourself as part of your homework. It's just it's here, so you might as well do it. It's just 2 examples that we're going to do in this section. That's it. But we have already done this just last time. So let's move on to example 3, which let's see, where is it? Okay. I think, okay, to solve the absolute function, to solve find the zeros. In other words, to solve the what happens when f of x equals to 0. In other words, the absolute value equation, which we have done this exact thing, okay, back in section 2.6. So please do this yourself as well. If you need to review section 2.6, feel free to do so. And sometimes when people have done some math and they did it and feel pretty good about it, and then a week or a month later, then they think about it again, they can't quite remember how to do it, and then they get really upset. It's like, I was so good at it just not that long ago, how come I don't remember it? But don't be upset about that. If something like that happens, just look it up, okay? It's no big deal. It happens all the time. So then in general, solving equations need to be reviewed constantly, especially if you tend to forget about it, which is I have this written down in this video description below, which is solving equations, which is section 2.2, the first 7 examples. After that, it talks about something else. So section 2.2, examples 1 to 7, and of course section 2.6, examples 1 to 11. That's all kinds. Those 2 includes all kinds of equations, the regular stuff, and then some unusual stuff such as absolute value function, square roots, and I don't know what all. Okay, so make absolutely sure that you know how to do 2.2 and 2.6 all the time. At any time you forget and you need to look it up, do so, and don't let yourself get upset over it. It's no big deal. If you forget something, look it up. People forget all the time. That's why we invented writing, so we can look up what we forgot. So, and then so that is the end of section 3.6. So let's move on to section 3.7. And as you can see, it's not that many pages later because I think the book forgot that they already did 3.6. So there is just a weird, short little section that shouldn't even be there. So let's move on to section 3.7, which is on page 296. Right? Yep, I'm right here. And then we're going to consider something called the inverse function. Now, the inverse function is something that takes the function back where it started. For example, let's define f of x as some function such as, I don't know, let's call it x squared, okay, a very common function. Then in that case, what happens is f will take, say, the number 2 will be taken to, the number 2 will then become 4, okay? And then the function, the number 2 will end up with 4, and the number 3 will become, of course, 9, and so on. Now, the inverse function is something that does exactly the opposite. That is, let's call it g of x. What does the exact opposite of x squared? That is, what function takes 9 back to 3 and takes 4 back to 2? That would be the square root. So we'll define g of x as equal to the square root of x. So then what happens is g will take 9, okay, kick 9 back to 3, and kick 4 back to 2. And now Now, what is that? That is, being oppositional, right? We'll do exact opposite of what you did. So that is, so when it's oppositional like this, these are things are called inverses. The inverse function is also written like this. That is g of x. You can write it as, so the inverse function of f, we call it g of x. We also can write it as f minus 1 of x. The minus 1 is over f only. Okay. Now sometimes you might say that if you, for example, if you say x to the power minus 1, right here, a side note, x to the power minus 1 is equal to 1 over x. But x is a variable. Okay. We have, right now we're writing the minus 1 right in front of f, which we have never done before. And so this then has nothing to do with 1 over something. This means the inverse of f itself. So then you have to figure out how to come up with something that does the exact opposite of that thing does. And when that happens, then they are called inverse functions. Inverse functions are not always exist or something, at least not in the whole sense. But, well, anyway, the point is this is these two in this situation, okay, are inverse functions. And that's what we're going to be talking about in this entire section. All right, so now that we know what an inverse function is, it just kicks everything from, it does the exact opposite, okay? It's called an oppositional. And so anyway, let's look at example 1, see what it says. Okay, now example 1 says that if you have a function such that f of 2 is 4 and f5 is 12, what does the inverse function do? Well, the inverse function then will take 12 and kick it back to 5 and take 4 and kick it back to 2. That will be this function f's inverse function. And that's it, okay? So that's that. So that's example 1. And then, however, that was a quick, simple question. But in general, let's say you have two functions. Let's look at example 2. We have, let's see, what is that? Say if we have a function that's like this, right? And then you have some other function that looks somewhat similar. And well, is one the other inverse? So are they inverse or not? So to check if some function is an inverse, what you're going to do is that you know that when you put a number, say 2, into f, it becomes 4. And then if you, then the inverse then will take 4 and go back to 2. Why do I have x here? I mean 2. Okay, this is 2. 2. Anyway, so the inverse will take the 4 and kick back to 2. So in general, when you if you put the inverse function into the original function, it should get x back. Because you started with x, and you got somewhere, and you put it in a new thing, you should get the x back again. So that's how we're going to find the inverse function. That is, to check if two functions are inverse, you will see if, say you have function f and function g, to check if they're inverse, you're going to pull this trick, okay? Given that you have f and g, you will calculate f of g of x. You're going to stuff the entire g of x to the input of f of x and see if this can go back to x itself. That is, did say 3 go to 9, did 9 go back to 3? If every single time, see? So you will stuff, so you take f of x and then do g of x, which should kick it back if it is an inverse, and see if we got back the original thing. And that's how we are going to do that. Now, in this case, we have, well, let me copy down the problem. So first, let's do f of g of x. That would mean put the entire g into the input of x and see what happens. So let's go through the work, okay? Let's see, 1 over x minus 2. So this whole thing becomes the new x. So let's write that out. Is 1 over, see, this used to be x, okay, plus 2. And we're going to stuff that whole thing in here. So that becomes 1 over x minus 2. And now we're going to do this fraction trick, okay? And then to do the fraction trick, we will have, I'll write it over here. This becomes, here's still 1 over. The big division line stays until it's ready to be flipped. So what we're going to do here, this will use the common denominator in here, which is 1 over x, okay, minus 2x, because if you, the common denominator will be just x, because when you cancel this out, then you get the minus 2 back, whereas this one stays here. And then that plus, we'll put 2 over x as well. As a result, we'll need to put another x there to be fair, right? Because when it cancels out, it becomes the 2 again. So then, so this is 1 minus 2x plus 2x, which is just equal to 1, right? So the whole thing under the denominator becomes 1 over x. All right, now to divide, when you do this kind of fraction, the long division line stands for divide. So this is dividing by that. And to divide by a fraction is to invert and multiply. So this will be equal to 1 times x over 1, which is just x. So remember, to divide is to invert and multiply. And if you have some concerns about doing fractions, please review section 1.7, I think, okay, until you get all the fraction stuff done. A lot of students have trouble with fractions, even though it's just something that you need to review all the time if you tend to forget it. So anyway, let's move on to, so that equals to x. And as we said before, if f of g of x equal to x, then that's it, okay? It got kicked back. So you stuffed something in there, okay? And it got somewhere else, and then it come back again. And we are also gonna do the other way. That is, what is g of f of x? And either one of these processes is enough, but we will, for the purpose of demonstration, do both, okay? Let's do both of these things. What is g of f of x? That way, so before we stuffed g in here, now we're gonna stuff f in on the other side as a g. So g of x is equal to g of 1, sorry, I shouldn't be writing down g. Okay, so g of x is 1 over this x, right? And then minus 2. But instead of x, we're going to put the entire f of x in here. And what was f of x again? F of x is 1 over x plus 2. We're going to stuff that whole thing in here. Okay, now and then see if this becomes x again. If it does, then we're good. Now, being that it did before, it's gonna do it again. However, we're gonna just make sure, okay? We're gonna trust no one and make sure that this is actually going to happen. And therefore, this will become, now this is a fraction, right? This is 1 divided by this fraction. This is the longer division line, means this is doing the major division. So to divide by a fraction, you invert and multiply. So this becomes just x plus 2 over 1, or x plus 2, okay? And minus 2, and that will be equal to just x. So when you do this trick, and it does go back, g of f of x does go back to x, that means you're done. Actually, in your homework section, you only have to do one of these things. You don't have to do both. And so as long as you get back to x, that means you got back to where you started. And so that is, so please do this example. What is it? Example 2 as part of your homework. Next, let's look at example 3 on page 298. We have f of x is x cubed and g of x is 1/3 of x. Well, is one the inverse of the other is the question? Well, we're going to do that by stuffing it in and see what happens, okay? So let's do f of g of x. F of g of x, then g of f of g of x, okay? And that equals to, f of x is normally x cubed, but we're going to put the entire g of x where x used to be, which is 1/3 x. So now we have 1/3 x cubed, and that equals to 1/3 cubed, okay? And x cubed. The exponent applies to each one, as chapter 1 teaches. So in that case, then we have whatever this is not x, okay? This has to become x for this to be inverse functions, and this is not it. So the answer is no. This is not inverse function of each other. So next, let's consider the domain and range. The domain and range of inverse functions will they will switch domain and range. For example, the function square root of x, okay, which has let's say if you have f of x equal to the square root of x, its domain, of course, is going to be from 0 to infinity, positive infinity, being that it can't take any negative numbers. So that is so the inverse function then, so its domain is here, okay, and then and its range is also from 0 to infinity. Here's the range. So here's the domain. We'll write down D, and the range we'll write down R to positive infinity. Now why do I have a bracket here? You're supposed to write parentheses. Anyway, so the inverse function is g of x equal to x squared, because x squared reverses the action of square root. Now then the g of x then has, for the purpose of being the inverse function of f, we have to restrict its domain from 0 to infinity and then go back. So in general, the domain and range for inverse functions, they swap, okay? Whatever used to be the domain of this guy now has to be the range for the other guy for things to work out. And then whatever is the domain of this guy, it will become the range of the other one. Now, of course, the natural domain for x squared is bigger than just from 0 to infinity. But as its inverse function, it has to restrict it, because this thing can only land in the positive side. So we can restrict the domain so that it matches the range of the inverse function. But anyway, so let's find the inverses. So next, let's look at the inverses. Example 4 on page 300. Okay, let's look at 300, and what are we trying to figure out? We're trying to figure out which function are one-to-one. So to find inverse functions, one-to-one is important, because if the function isn't one-to-one, then it's hard to figure out which way you're coming back, and to find the reverse situation. For example, let's look at example 4. Okay, so at the first example 4 on page 300, on the top of the page, we have a bunch of functions that we looked at before and also graphed. Where the first one being f of x equal to x. Now that one, the inverse function is itself. Okay, I mean because it doesn't go anywhere. F of x is just x, so the inverse function f of inverse of x is still x. Okay, it didn't go anywhere both directions. It stayed put. So f of x equal to x is the identity, called the identity function. It's identity because it became itself, so it got nowhere. And then so the next function is the quadratic function, which is let's see. And let me see what your book wants. Give me a second here. Now, in general, the concept of one-to-one matters for inverse functions in the sense that if a function sends two things to the same spot, then it's hard for the inverse to figure out how to come back. Like, for example, right here. For example, this one, if we restricted the domain from 0 to infinity, because if you let it have the entire domain, that is all the negative numbers as well, then what happens is for the g of x equal to x squared, we have, we have g of 2, right? It will become, of course, 4. But then of g of negative 2, g of negative 2 then is also 4. So then what happens with your inverse function? Should it go back to 2 or negative 2? Then you got a confusion. See, that's why the inverse functions are normally restricted to when it is one-to-one. So if we restrict it to only positive numbers for the domain of g, then this one we do not consider this one. So then all the inverse functions go back to just one value. That's why to find inverse function, we need the original function to be one-to-one, at least in a limited area, so that we can find our way back instead of not knowing which house to land on. Okay, and so then so let's look at page 300, where your book mentions something, so we'll go over it briefly. The constant function is not one-to-one because the function just equals to some constant. So f of, for example, f of 1 equals to maybe 5, okay? And f of, say, f of 10 is also 5. In fact, f of anything is 5. That's because it's a constant function. It always equals to 5. So then when you, if there's an inverse function, where's it supposed to go back? You have no idea. And so then the constant function does not have an inverse because everybody's going to the one spot, so they don't know how. It's hard to say which way to get back. Okay, so the inverse of 5 is what? Is it 1, 10, 20, or a zillion other things? So the constant function you cannot get an inverse for it. And the next thing the book mentions, the absolute value function. It is not a one-to-one function, right? The absolute value function looks like a v. However, if we restrict it to only half of it, like say only the positive part, that is the half that's positive, and above the, I mean, where x value is positive. I don't know if you can see what I'm doing. It's or if we restrict it to the other side, say only the negative part, then might be okay. For example, in your book says the absolute value function, if you restrict the domain to just from 0 to infinity, the positive part, then it is, which then makes it the same as just the identity function, then it's okay. And then the reciprocal squared function is similar. Okay, here's the reciprocal squared function, that is 1 over x squared is this thing. And you see that it's not one-to-one because remember how the test for one-to-one, you draw a straight line right across, okay, the graph. If it hit it twice, then it's not one-to-one. If you only hit it one time, then it is one-to-one. And this is on page 196, the horizontal line test, which I have also typed in below the video description. So you can look it up if you don't remember it quite that well. So then you see, so so any function that is not one-to-one, you can ignore the part that part of it, okay? Let's say if you ignore the part I covered and just only think about the positive side, then it is one-to-one in that restricted area. Or you can also restrict this side, of course. There's no reason which side you're restricting. But either one will, if you restrict it, then it becomes a one-to-one function in the restricted sense. And then you can find an inverse function for it. So next, let's look at the next problem. Okay, the next one on page 301. Let's look at. Give me a second here. On page 301, let's look at example 5, where we have a table. Okay, now the table shows some function. All right, we need to, well, all right. So let's just stare at it. Okay, now we have a table of a function that's in table form only, and its domain consists of 4 options that you have for t, and then there's f of t, and the question is, what is the inverse of f inverse of 70? That means when ft is 70, what is t? Can you find it? Well, you can look down here. What's 70? When f of t is 70, t is 90. So the answer, f inverse of 70, is 90. And that's about all. So next, let's look at the inverse. Okay, example 6. Okay, where we're supposed to find g of 3 and g minus 1, g inverse of 3. Example 6. So let's look at page 302. Where's g of 6? G of 3. Okay, let's see. Here's the example 6. Okay, we'll just stare at it. To evaluate g, we're supposed to find g of 3 and then g inverse of 3. They are not the same thing. Okay, so g of 3, so when the value of g at 3, so we look at 3 and then look up, and what does it say? 1. So g of 3 is 1. That's easy enough, right? What is g inverse of 3? G inverse 3, we need to look up where g becomes 3. It becomes 3 at, look across, it hit the graph at, then look down at 5. So g inverse of 3 is 5. That is, when does g become 3? When the value is 5, then then g becomes 3. In other words, the reverse is that g inverse of 3 is 5. So that's what g does. And that is the answer. Next, now let's, okay, so let's look at example 7, okay? And then we are going to do something. We have, let's see, what are we given? We are given for a formula, find a formula for the inverse function that gives Fahrenheit as a function of Celsius. All right, so we have a Fahrenheit to Celsius conversion function, okay? Here is the function. So if you have a Fahrenheit, like say you're 90 degrees out, and because you're living in Florida, and then you plug it in and do this thing, then they'll give you what the Celsius, that is the metric system, it calls 90 degrees. It's probably 34 or 32 or something like that. But anyway, that is the inverse function. But what if we want the reverse formula? I want to give the C and then give me the F. That would be the inverse formula. And we're going to do that by, by doing solving equations. Let's see. All right, so let's look at, let's write down, let me first write down what I'm talking about here. All right, so we're now on example 7, page 303, where we need to solve for f, okay? We need to plug f out, so the f equals to something in terms of c. That way people know how to plug in a c and get f. Right now, we can plug in f and get c. But I want something where we plug in the c and then we get f out. So we need to pull this thing out. And we're going to do that by solving the equations. So this equal to, we'll multiply the 9 over here. Okay, so it becomes 9c. Now we're just solving the equations. And as I mentioned before, solving equations is in section 2.2, the first half, and section 2.6 if you need refreshing your memory on how to do this. So this will multiply the 9 here across, so it goes up. And then 5f, multiply the f times 5, and then 5 times 32. 32 times 5, okay? The dot means multiply. And then the next thing we're going to do is, what are we doing? We are isolating f, okay? We want f to stand alone, get rid of everything around it. So we have 9c plus 32 times 5. I will multiply this out later, okay? This equal to 5f, right? So which means the f is equal to all this stuff divided by 5. We'll get rid of that 5 there because we pushed it all the way down here. So let's, and that would be equal to, that would be the formula for f. Another way of writing it would be 9 over 5c, okay? I'll split the fraction back in 2 chunks, and 32, I'll cancel out the 5. That will be plus 32. Okay? That will be the formula for, if somebody want to plug in a c and get the f out, that they will use this formula. And if somebody wants to plug the f in, the Fahrenheit, and know what the Celsius is, they will use this formula. And they're the exact opposite of the inverse of each other. So that's what it means by having an inverse function. So next, let's do something else, okay? Example 8, solving to find an inverse function. Now, f of x equal to, let me write this example down. All right, so now I have the problem 8 written down. So f of x equal to this thing, we need to plug x out, okay? I need to isolate x, just like the way we isolated f out of that equation. We need to isolate x. We'll call f of x y because we don't want to write all that stuff, okay? We'll just call it y. So our equation is, let's pull this thing out. So first thing we do is subtract by 4. Get rid of 4 from that side. Eventually, we're going to get rid of everything from that side except for x because we are trying to isolate x. So that we have 2 over x minus 3, okay? And y minus 4 is the same as y minus 4 over 1, okay? And then because x is on the bottom, I'm going to flip both sides at the same time. So we have x minus 3 over 2. And then this will be 1 over y minus 4. because I like x on top, okay? Being in the denominator kind of is annoying. So being that they're both fractions, right, then you can flip them both at the same time with the logic that, that say if you 3 over 5 equals to 3 over, say 6 over 8, let's say, then you can flip it, right? 5 over 3 then equals to 8 over 6, see? Because if the fractions are the same, then flipping it doesn't, they're still the same. So that's the logic behind the flipping. Now, we have done that. So next, we are going to continue, okay? Let's put the 2 here on top over here. So we have 2 over y minus 4 is equal to x minus 3. Okay, and then we will move the minus 3 to the other side. So finally, we have x equal to 2 over y minus 4. And then the 3 moved to the other side becomes plus 3. So we have 3 plus, my 3 looks weird, but it's a 3. All right, so then that should be the solution. Now let me check if I get it right. X equal to 2 over y minus 4 plus 3. Yep, so that is the answer. That's the reverse function. Now, okay, so the inverse function then, if you write it the other way, see, right now we're doing x in terms of y, but if you write the inverse function answer is often, they turn the y back into x because it's a different function. So the inverse function then we will write it as f inverse of, so f inverse of y is equal to this equation, which is what we have down there. But you can also write it, replace the y with x, because people like x better than y. No other reason, okay? X, y, same thing. Doesn't matter. It's just the input variable. So you can replace y with x so that we get our x back, and people like x's. So, but you don't have to. You can just keep it as y. That's fine too. Okay? It's the inverse function, and whether the variable is called x, y, w. Apples, oranges makes no difference. Anyway, so next, let's look at the next example, which is a very similar problem. As you notice, what we're doing here is we're basically like solving an equation. Is basically what we're doing, which is why I keep mentioning that if you have trouble solving equations or sort of forget some of it, please don't hesitate to review the section. Not all algebra need to be revealed like this. It's just that, just those, just chapter 1 and those 2 parts I mentioned in chapter 2. And if you keep reviewing it, it's just you're going to be, you will enjoy algebra a lot more, okay? I mean, a lot of people hate math because they don't know how to do it. Math is always easy once you understand it, or if you forgot it, once you remember. So next, let's, what's next? What is that? Then when we're doing, oh yeah, example 9. So let me erase the board. Next, let's do example 9, where we find the inverse function. But before that, I forgot to mention what happened to SpongeBob. Right now, winter has come, so I need my SpongeBob because it is actually a warmie. See right here? I don't know if you can, let's see, let me put it here so you can see. Yeah, it is a warmie, which means you can microwave it, and then it gets warm and keeps me warm. So I need this thing and can't let it hang out by the board anymore. So I will put SpongeBob back when spring comes, but I want to explain it to you because some students get really, really upset when the doll is missing. Okay, so then let's move on to example 9, where we're looking for, we need to isolate x, okay? We're getting to get the inverse function. So then first we will do this trick, okay? That will be equal to y, because we don't want to write f of x all the time. And then being that that's y, then let's move that over there, 2, okay? That becomes y minus 2. Y minus 2, okay? And then this will be the square root of x minus 4. All right, then now we're going to square both sides. To square both sides, then this becomes y minus 2 squared. And then this is x minus 4. And then eventually, then x then equal to y minus 2 squared. We're going to multiply that out. That becomes y squared. Remember how this thing, y squared minus 4y plus 4. Remember how this works, okay? Or you can just write it out and multiply it. This is a formula, but if you don't remember it, just write this out and multiply it the old-fashioned way. Either way, that's what you're going to be getting. And then plus, and this negative 4 will be put over here. Clear over here, okay? It becomes a plus 4 when we move it across the equal sign. So this is y minus 2 squared, so everything should be good. And then, so x then equal to, the solution is x equal to y squared minus 4y, and then plus 8, and that should be the answer, okay? Do we have that? Next page. Right now, so the next page is, well, your book didn't even bother multiplying it out, which is okay too. You can totally accept this thing plus 4 as your book shows as the solution, which then, and then of course to write it in the x form. So then, see, the solution is x equal to y minus 2, etc., right? But you can change the variable to x because people like x better. So then the inverse function of x can be written as x minus 2 squared plus 4. Now the domain of this thing, now we'll talk about the domain slightly. The domain of this function is x has to be bigger than or equal to 4. Okay, and or write it the notation way that the book likes is 4 comma infinity, with the bracket means 4 included. Now the range then, but the reverse function here, you can take anything, right? But we will, but the book wants to be careful and just not so much careful, but a stickler, and just say that we'll limit the domain of this thing to the range of that. Now, what is the range of this function? The range of this function can go from 2 to infinity, because at when x is 4. This value will be 0, right? And anything else within the domain, it will be bigger than 0. So the range of this function goes from 2 to infinity, and your book wants to restrict the domain to just from 2 to infinity, because that's the range of the original function. That is, anything coming from this function can only land in here, so the inverse function can only pick up stuff from here to go back. If it picks up something else, it will, I don't know, it's like, it's not the inverse function anymore. So to be the inverse function, its domain has to be restricted and then it will map stuff back. That is just, but that's not really that critical of a detail, I don't think. I should, but I want to mention it. So let's look at the next thing. Okay, now the inverse function, as we mentioned, is what they basically do is exchange the x and y value. For example, if you have a function where x gets sent to y, okay, the x value goes to y value. What the inverse function is then send the y value back to x, and as a result, what used to be a point x, y, on the original function graph, xy, in the graph, the inverse function, it will look like yx. And because of this flip, what happens is that the inverse function has this interesting quality. That is, if you have a function of f like that, okay, the inverse function will be the mirror image of the original function if the mirror is that cross-section line. The y equals x line, you know, there's the one that goes at 45 degrees. Yeah, and if you look at it, I don't know, this way. Yeah, I'm trying to get the orange line vertical. Yeah, if you look at it that way, you notice that the inverse function is like a mirror, and the two sides are completely perfect mirror image of each other. And that's how you graph an inverse function, is you graph the original function, then you flip it onto the mirror image. And this is why the reason is, because for the inverse function, you effectively are exchanging the x and y coordinates. So let's do one of these things, okay? What is that? Example. So we're looking at example 10, where we have the graph is given to you like that, okay? And so I will draw the graph here. So here's example 10, and I drew the graph in your book right here. And then so the goal is to draw the inverse function of this thing, which means I'm going to draw the y equal to x line, the slanted line, and then tilt my head and try to draw this thing as the exact mirror image of the other thing. Okay, so let's do that. Now this is the mirror image of this line, the x-axis and the y-axis. So with the lines help, you notice this line never crossed the y-axis. So this thing will do something similar and never cross the x-axis. Okay, yeah, something like that. Not that good, but your book has a better drawing. Yeah, much better. See, let me make, you can look at your book, of course, but I will just show you real quick. See, the green line looks pretty good. So that's the inverse of the original blue line, which is f of x. And all inverses are that way. You just flip it like this. That's it. And then you got your inverse. And okay, so and so next, let's next, that's it. That's example 10. So please do all the examples in this section for your homework, like always. Now remember, doing examples is extremely important to be good at math, because the examples show you how to do something, but it would be better if you actually practice it yourself, not just watch the examples or watch the teacher do it. That is basically the only way to be extremely good at math. And yeah, I mean, I'm not just saying this lightly. It sounds like a simple thing to do, but not many people do it. I don't know why, but the ones who do it gets very, very good at math. I mean, I graduated with a math degree, right, with the highest honors, and this is my secret. Okay, I'm telling you that to hope that to inspire you to do the examples. I know it maybe sounds a bit tedious. You think, well, you already explained it to me. I know how. Why do I have to do it again? It's important, because when you do it again, then you realize there are parts of it that you might have missed, or you just you're sort of incorporating it into your own being, so that now it's a part of you. Okay, to do it yourself. So please be sure to do all the examples that I ask you to do, as well as the homework, of course. The homework for this section is problem 6, 11, 15, 18, 21, 23, 27, 29, 31, 35, 37, 39, 43, and 45. And most of them are quite short, so it shouldn't be too much bother to get them done. So please do your homework, and when you're done, I want to talk about some of them. Now that you're done with the homework, let's talk about some of them. First, I want to talk about problem 15. So now problem 15 says we have f of x equal to x squared minus 5, and we need this thing to be non-decreasing. That is, it should at least not be decreasing. That way we can make it into a one-to-one function. Now f of x squared minus 5, you can draw it quickly. I think it's just f of x squared and knock it down 5 steps, okay? And like this. So it's non-decreasing starting at 0. So we'll restrict the domain from this point onward. Also call it from 0 to infinity, okay, including 0. That way the function is just this part is a one-to-one function with a restricted domain. Then we can find the inverse for it, because when x, well, we'll see that in a second. So let's find the inverse, okay? Okay, so then we have, so as always, we write f of x equal to y, and then solve for x. That is, we're going to isolate x. So that equal to y plus 5, move the 5 to the other side, and then x then is equal to the square root of y plus 5, where y had better be bigger than something. So y plus 5 has to be bigger than 0, because y plus 5 is bigger than or equal to 0, so that the square root makes sense, okay? Because then y then better be bigger than or equal to negative 5, okay? So that is the domain of the inverse function, but we actually don't care about that right now. We just care about the domain of the original function if it's, right? Yeah, so the inverse is is this function, and that's the domain of the original function, such that you have an inverse. Okay, if we ignore that part, then any horizontal line test will not hit the graph twice. Okay, so just block that part out, and then we can have the inverse. And that's problem 15. Next, let's look at next, let's consider problem 21, which is f of x equal to minus 5 of x plus 1. Is this function 1 to 1? Well, this is a linear function, okay? The book says you should graph it and take a look. Let's not bother graphing it. It's just a linear function, which means it's a line, okay, going, it has a negative 5, so it's probably going down. Doesn't really matter. The point is, if it's a linear function, as long as it's not constant, it is a one-to-one function because it's a straight line going some way. That isn't level, okay? A constant function is a line that's actually level, which we're not going to be able to get the inverse function out of. But as long as it's not level, okay, you only hit it once. And therefore, regardless of what this thing looks like for sure, we'll say that this thing is 1 to 1, and that's the end of our answer, which it is, okay? And so next, let's look at problem 27. So we're trying to find the inverse f at 0. Now, to do that, we'll start with a y value. And y value has to be 0, okay, which is right here. And then figure out where it hits the graph. What's the x value? That's 2. Therefore, the inverse at 0 is 2. As if you start at y, then you get to the right answer, which it is. Okay, now problem number 43. We need to find the inverse of this function and also graph it. So this function, this is x to the power 3. We know that it looks like this, okay? And then it got subtracted by 1s, which means we push it down 1. And then we will draw it by pushing down 1. All right, so I pushed it down slightly. That's the inverse function. And then that's the minus 1, okay, from x to the power 3. I should probably write that down. This is x3, and this is x3 minus 1. All right, now to do the inverse function, remember we're going to reflect this thing across the y equal to x line. This is our mirror, okay? And then so to reflect it, it would not be easy to draw. Something like that, okay? This is the original, well, something like that. It doesn't go down though. It should still go up. Well, anyway, if you graph this in Desmos graphic calculator, it'll create a much more beautiful picture. Or look at the answer in the book. Either way, okay? But for now, let's calculate the inverse function. To do that, of course, we have to, write y equal to f of x, and then and isolate x, okay? So then that move the 1 over here, becomes a plus 1. You always change the sign when you move numbers across the equal sign, and then that is x cubed. So we'll get rid of the cube by taking the cubic root of both sides. So then we have 1/3, okay? And then this is also x. So because I took the cubic power, so then this becomes 1/3, and that should be it. That is the inverse function. Now let me see. So then x equal to y plus 1 to the power 1/3 is the inverse function. But the book seems to like calling it x instead of y. So therefore, we'll call the f inverse of x. Okay, so instead of y, we'll call it x and say x plus 1 to the power 1/3. And that is the inverse function to the original function x cubed minus 1. And that is the end of this section.